Now coming to the next part, reversible process and irreversible process. Now you have heard it in lower classes. You have read it also. What is reversible process? A reversible process is a process which can be reversed by reversing the experimental conditions. That is a reversible process. Irreversible process is a process which cannot be reversed. Even if we reverse the experimental conditions. That is called as an irreversible process. We can say that. Got it? Now here the reversible process is similar only. It is similar. The concept is similar, but it is the definitions, or I should say, in this context, it is slightly different, which I am going to say. Got it? But the concept is similar. Here also the reversible process can be reversed by reversing the experimental conditions. Got it? It can be reversed. Here the reversible process takes place in phases, in small steps, in infinite number of steps. And remember it, reversible process never tends to get completed. Never tends to get completed, reversible process. It is always at equilibrium, reversible process. Alright, remember it, these points. It is always at equilibrium. It never tends to get completed. It is always completed in small steps, infinite number of small steps. A reversible process. We can say, I don't say it completed, I say that reversible process takes place in infinite number of small steps. You can say that. Got it? In case of reversible process, you will find a part of the reaction, if it is carried out in the forward direction, then in the next moment, a part of the reaction is carried out in the backward direction. That is called reversible process. It is reversed, we can say that. But irreversible process, it cannot be. We cannot get it, this particular conditions, we can say that. Now, coming to the reversible process here. A reversible process is a process which is carried out infinitesimally slowly. Very slowly the reversible process is carried out. For that purpose, sometimes we feel that a reversible process is static. That means it has come to standstill. No more reaction is taking place. No more process is carried out. It has come to standstill. Sometimes we feel. Why? Because the reversible process is very, very slow. What I said you? A reversible process is a process which is carried out infinitesimally slowly, so that all the changes occurring in the direct process, all the changes which is occurring in the direct process can be exactly reversed, and the system remains almost in a state of equilibrium with the surroundings at every stage of the process. I have already said you this point, that reversible process never tends to get completed. Reversible process always, it has a state of equilibrium with that of the surroundings, we can say that. So reversible process is a process which is carried out infinitesimally slowly, so that all the changes occurring in the direct process can be exactly reversed. It can be reversed, and the system remains almost in equilibrium, in a state of equilibrium with the surroundings at every stage of the process. That is called as reversible process. The system is always in equilibrium with that of the surroundings. Here we are having two things, system and the surroundings. Alright, so always it is at equilibrium with that of the surroundings at every stage of the process, and it is a very, very slow process. We can say that. It never tends to get completed. Clear? Now, but on the other hand, a process which does not meet the above requirements, means it is not slow, it is the reaction is not reversed, we can say that. It is not at equilibrium, alright, above conditions which I said, the above requirements, then that is called as an irreversible process. That particular process is called as an irreversible process. So an irreversible process is defined as that process which is, what you can say, not carried out slowly, rather it is fast, the process is rapid, the process is, for example, burning of a paper, a piece of paper. Combustion, any sort of combustion is an irreversible process, we can say that. Got it? So that the successive steps of the direct process cannot be retraced, means cannot be reversed at any change. Got it? And any change in the external conditions disturbs the equilibrium of this particular process. Any change, suppose in middle of the process, if you disturb the process, if you change the conditions, alright, then it disturbs the equilibrium of the process. For example, a certain thing is burning. Got it? If you remove the heat, if you remove the energy, then will it burn completely? No. It will not burn completely. It will burn partially, we can say that. The combustion will take place partially, we can say that. Just an example I am giving you this one. So in this way, that is an irreversible process. So an irreversible process defined as that particular process which is carried out, which is not carried out infinitesimally slowly, rather it is a fast process, a rapid process, that particular processes. So that the successive steps of the direct process cannot be retraced, cannot be reversed, we can say that, and any change in external conditions disturbs the equilibrium of this particular process, any change. Now, to understand this particular reversible and irreversible process, I will tell you a particular, that is experiment. I do an experiment and I will explain you. Here I have taken, that is a container which contains some gas in it, and this is a piston, a metal plate. This is a metal plate and I have kept a piston here. That is, I have taken a piston here, and here also I have put a small container to put some object in it. Let us say some weight or something like that to put there. I have taken it. You can put it in here also, a plate, you can put it there. Fine. So here what is that? A gas is there. This is a metal plate, I said it. Alright, and we have what you can say, this is a piston, we have put it. Now external pressure, this is your external pressure, we can say that. Let me write it this way. This is a P external, the external pressure which is acting downward, and here this is the internal pressure, we can say that. External pressure and internal pressure is very important, very important. So what I am doing is that initially this is at equilibrium, we can say that it is at equilibrium. Here the P external is equal to P internal, it's at equilibrium. Now how it is at equilibrium? I put some sand here in it. I put some sand. That means I have given some external pressure. I put some external pressure here. Alright, listen here. I put some sand, a pile of sand, it is there. This is a pile of sand. I put it here. A pile of sand, I put it. Alright, here we can see that. Now I will put that much sand only when it remains equilibrium. I will be slowly and slowly putting some sand into this metal piston, we can say that. Alright, so you will find sometimes it goes down, this metal plate. Now if you leave it, it again slowly comes up. Due to internal pressure of the gas, it comes up. Now at a particular point it remains equilibrium. Okay, fine. Now listen carefully. Here what will I do? I will just take out few particles of the sand from here, from this metal plate. Just I will take out few particles of the sand. What you will find? The external pressure is going to decrease. External pressure decreases. I will take out few particles. As I will take out few particles of sand from it, you will find that again the piston goes up. Got it? Again the piston goes up. Alright, again it comes down. It balances, and at a particular point it remains again at equilibrium. Alright, when I take out some few sand particles from here, you will find definitely the internal pressure will be more because the external pressure will decrease. So what you will find, this particular metal plate will go up. It will go up, but it does not mean that it will go up to a large extent, because you will not take out a big amount of sand. Alright, just few particles, I said few, 2 to 3 particles you take it out. So external pressure slightly you decrease it. You will find slightly it goes up. Alright, it slightly goes up. It goes up, again it comes down, again it goes up, and finally it attains an equilibrium. Alright, now again what you do is that again few more particles, just few, another 2 to 3 particles, again you take it up. Again the external pressure is going to decrease. Again you will find it is going to move up. Internal pressure will increase, it is going to move up, and again it will go up, down, and at a particular point it comes in equilibrium. It attains equilibrium. What is this? Alright, it's a reversible process. I said that. It's a reversible process. Again you put some more sand into it. Again you will find the external pressure will be slightly more than internal pressure. Again it will go down. It will go up and down. It will swing little bit. And after a particular point of time, it will remain in equilibrium. It attains equilibrium. So that is a reversible process. So this process is reversible. See, I can reverse it. I can put some sand, I can take out some sand, and I can change the equilibrium of the process. Alright, I can change the equilibrium of the process. So that is called as a reversible process. Now this particular condition cannot be achieved in an irreversible process. But this is very slow. Alright, as I said, it will go up and down and then it will come. Do you think it is going to be very fast? In this way it will go and it will remain. No, slowly it will go up, slowly it will come down, again slowly it will go up, and at a particular point after a long time you will see it remains in equilibrium. Till that time you will see either it is going up or down, and hence at a particular point it will remain in equilibrium. So to happen this, it will take a large time, a long interval of time is going to take it. A long interval of time. For that reason I said this process is very, very slow. It is an infinitesimally slow process. And it takes place in several stages, we can say that. And in each stage, it attains equilibrium, we can say that. Clear? I hope it has been clear to you. That's a reversible process. It's carried out infinitesimally slowly. At any stage during the process, equilibrium, what you can say, is not disturbed, we can say that. Got it? It takes place in infinite time. It takes place to complete the particular process. Rather, I should say, we cannot wait for infinite time. For that reason, I said that a reversible process never tends to get completed because it's not possible for us to wait for infinite duration of time. It is only imaginary and cannot be achieved in actual practice. That's a very important point. In actual practice, are we going to wait for infinite length of time to see whether the reaction is attaining equilibrium or not? No. In actual practice, it is not possible. So in actual practice, all processes are what you can say irreversible. We consider it. All the processes are irreversible because we cannot wait for infinite duration of time and to see whether the process is attaining equilibrium or not. Alright, so work obtained, it's a very important point, you may note it down. The work obtained by this process is maximum in case of reversible process. It is maximum. But in case of irreversible process, the work done or the work obtained is not maximum. When I teach you about the work, I'll tell you how the work done is maximum in case of reversible process. And in case of irreversible process, the work done is less compared to reversible process. It is not maximum. I don't say it is minimum, but I don't say it is not also maximum. The work done by irreversible process is less than the work done by a reversible process. We can say that. Clear? I hope it is clear to you, all these things. Next, we will come to that is internal energy, denoted by the letter, what I said, internal energy, denoted by the letter U, capital U or capital E. I am going to use as U. Alright, because E means energy also it comes, so it's better to use as U. Alright, I am going to use this. Now, what is internal energy? Internal energy is nothing but the stored energy in a particular system. It is the sum total of all the energy present in a particular system. Sum total of all the energy means there are many different forms of energy which is there in a particular system. It is heat energy, light energy, sound energy, rotational energy, vibrational energy, oscillatory energy, mechanical energy. In this way, different types of energy are there in very minute quantities, we can say that. So, internal energy is a sum total of all these energies present in a particular system. That is known as the internal energy. So, the energy, for that reason I said, the energy which is stored within a particular substance, within a particular system is called as an internal energy. We can say that. From the word itself, we can come to know what is internal energy. The name itself, we can come to know what is internal energy. Alright, so it is associated with a definite amount of what you can say energy. We can say that every substance is associated with definite amount of energy, and that energy is called as the internal energy. But let me tell you again, you can note it down this particular point, but it is not possible to find the absolute value. It's not possible to find the absolute value because it involves certain quantities which cannot be measured. Alright, like what I said you, there are different minute forms of energy which is present in internal energy. So it is not possible to measure the exact value. Absolute value means exact value of internal energy, because the energy, certain energies are there which is not possible to measure. We are taking to be as constant. We are considering a particular number and we are taking to be as constant. Alright, like vibrational energy, translational energy, rotational energy, oscillatory energy. Got it? So in this way you find that the major forms of energy can be calculated: potential, kinetic, heat, light, sound. This can be calculated. But rotational, vibrational, translatory, oscillatory, these energies which are present in very minute quantities, we take it a particular value and take it to be as constant. So hence, for that reason I said it is not possible to calculate the absolute value of internal energy, the exact value of internal energy. Remember it. Clear? Because many minute forms of energies are being present. Got it? So that is, we also don't require the absolute value also. What you can say, the internal energy possessed by any particular substance, we also don't require it. We take the value which is we are getting it, that particular value only we are taking it. Why? Because we generally measure the change in internal energy of a particular system. We don't use the internal energy, we measure the change in internal energy. Why? Because internal energy is a state function. I told you already what is state function. State function which depends upon the initial and the final state. So hence we measure the change in internal energy, which is delta U. So delta U is equal to U2 minus U1. That is final internal energy minus initial internal energy. Final minus initial. So hence when we measure delta U, for that reason we are not concerned at what is U. We always use delta U in solving the numericals, in solving the problems. We don't use what you can say U. You can also write it in this way: UP minus UR for a particular reaction. I am saying UP minus UR. P is the product and R is the reactant. So internal energy of the product minus internal energy of the reactant will give you the internal energy of that reaction. We can say that. Got it? That is delta U, so to say. Got it? For that reason, as it is a state function, got it? As change in internal energy as is a state function. As internal energy is a state function, for that reason we calculate the change in internal energy, and this value we use it, this particular value we use it. Got it? So absolute value of internal energy is not required also. Got it? So understood, internal energy is a state function, and energy, as I said, you have read it also, that internal energy is also what you can say, that is nothing but it is extensive properties. It comes under, we can say that internal energy, we can say that. So in this way, internal energy, in terms of internal energy, when we say, we calculate the change in internal energy. Got it? Fine. So energy is measured in what? Joules. So unit of internal energy, SI unit is joules and CGS unit is erg. Now internal energy depends upon the quantity of the substance present in the system. I said you already. So hence it is what? It is a extensive property, for that reason. Internal energy of ideal gases is a function of temperature. For ideal gas, it's a function of temperature. Hence, in isothermal process, listen carefully. Hence, in isothermal process, as the temperature remains constant, there is no change in internal energy. So, delta U is equal to 0. You may note it down. For isothermal process, del U is equal to 0. Because for an ideal gas, internal energy of an ideal gas is a function of temperature only, because it depends upon temperature only for an ideal gas. We can say that. Got it? You have read it in the previous chapter that it's ideal gas. Gas is considered to be ideal gas when the temperature is high and the pressure is low. We have already studied here. So it is a function of temperature, the ideal gases. So as it is a function of temperature, when the temperature will only remain constant, so change in internal energy will be 0. That means when the temperature is not going to change, how the internal energy is going to change? How the internal energy is going to change if the temperature is not changing? So as the temperature remains constant, so internal energy is also, what you can say, delta is also 0. Definitely. For example, suppose a particular reaction. Now, initial temperature of the reaction and the final temperature of the reaction remains the same. Then, in that case, what you find is that is, if it is an ideal gas, is the reaction taking place? Is the reaction happening? No. So, delta U is equal to, what is that? It is 0. UP minus UR. Internal energy of the product and internal energy of the reactant remains the same. So, hence, delta U is equal to 0. That is about your internal energy, so to say. Okay? Thank you.